Have you ever experimented gravity? For example, when trying to ride a bike for the first time and falling again and again? Or have you ever played with magnets as a child? I'm sure that the first time you saw those little metallic objects attracting each other, you got really surprised. Usually, when children are totally driven crazy by an event or natural effect, they start to ask a lot of questions repeatedly. In a funny way, they continuously say, "Why?" Although this might seem a childish approach to reality, it turns out to be very deep when trying to investigate a phenomenon. As a matter of fact, physicists tend to use this method to build appropriate mathematical models that can describe how objects behave in different situations. They need to build up laws that can predict the outcome of an experiment, and if they find an event that doesn't match their theories, they start to correct their beginning principles. And what do we have discovered thanks to this endless research? Where did this method bring us to? What governs our world? How can we resume all the existing sciences in just a handful of different types of interactions? These puzzling questions are the topic of this video that will present to you the 4 fundamental interactions that describe why our world is like the one we observe. Do you want to know more about this? Stick with me, and I'll tell you everything in a moment. Today, we are talking about the deepest theory in the entire history of modern science: Standard Model. What is that? Actually, it's the best model we have to describe nature, basing on 4 main interactions between particles. In order to make everything easier and probably more interesting, we need to take a little step back, forgetting about particles. Let's try to introduce each force in a simplified version, and then we'll discuss about bosons, fermions, and other incredible things. Firstly, each one of us can experiment gravity daily. If not, well, you're probably an astronaut orbiting around Earth in the International Space Station, but I think this is very improbable. However, gravity is the interaction that attracts us to the ground, and even the same that makes planets orbit around stars, like the ones in our solar system that seem to endlessly revolve around the sun. What is the easiest description of gravitation? Well, Newton may help us, saying that gravity is an attractive interaction that happens between objects with a defined mass. The gravitational force is inversely proportional to the square of the distance between the two objects, and directly proportional to the masses through the well-known gravitational constant that's around 6.67 times 10 to the negative 11. What is the second force everyone will surely know? Electric force. To be more precise, electric interaction alone is not a fundamental force. In physics, we have discovered that electricity and magnetism are 2 sides of the same coin, so we call it electromagnetic interaction. Therefore, don't worry, we'll discuss it later. Electric force has nearly the same proportionality of gravity when dealing with distances, but the constant, also known as Coulomb's constant, is way bigger, nearly 9 times 10 to the 9th. Moreover, electric interaction doesn't depend directly on masses, but on charges. Electrons have negative charge, neutrons have 0 charge, and protons have a positive charge. As a result of that, this force can either attract, charges of different sign, or be repulsive, charges of the same sign. This interaction is what makes electrons orbit around the nucleus of protons and neutrons in atoms. Probably fluctuate would be a better term because of quantum mechanics has shown that we can't know the exact orbit of an electron revolving around the nucleus, but this is another story we don't have to deal with right now, so we'll use this simplified description. However, electrons and protons have a small, but not null mass, so an interesting question might be, what influences atomic particles more, gravity or electric force? Since Coulomb's constant is way bigger than the gravitational one, electric interactions are billions of billions stronger than gravitational ones. A pivotal application of this interaction is obviously electricity that has revolutionized the entire world, changing our lifestyle and boosting technological research for experiments. But do you know what shocking phenomenon happened in the 19th century? Physicists observed that electric wires interacted with each other, and slight changes in current made magnetic compasses turn around. Briefly speaking, they understood that electricity and magnetism were 2 different aspects of one unique interaction, electromagnetism. In the second half of the century, James Clerk Maxwell collected in just 4 incredible equations the entire knowledge about this interaction. Surprisingly, from these 4 laws, we can derive the existence of electromagnetic waves like UV rays, radio waves, and light. Yes, light. The entire optic theory firstly developed by Newton was just a consequence of Maxwell's equations. At this point, physicists thought that all possible phenomena could be explained with either the gravitational mechanics and dynamics of the Newton or the electromagnetism of Maxwell. But as it always happens in science, some problems emerged in the description of effects like the photoelectric one, a radiation that is able to free up the electrons of a metal, and the black body radiation that brought to the establishment of the most revolutionary theory of physics, quantum mechanics. We don't need to dive deep into this topic. Let's just say that Einstein understood that electromagnetic waves could just carry discrete values of energy and called them photons. The intensity of radiation is linked to the number of photons emitted, whereas the energy of a single photon depends on the frequency. Red light is less energetic than blue light. Quantum mechanics has clarified that the electromagnetic waves and particles in the general can be considered both as waves and particles, depending on what the situation is. What is the name of the third fundamental interaction? Strong interaction. Yes, it's funny to hear, but this name is appropriate, and now we'll understand why. It is responsible for the strong force between neutrons and protons. As a matter of fact, very precise calculations have shown that the repulsion between protons should make them move away and destroy the nucleus, but fortunately, this doesn't happen. Why? Because the interaction between neutrons and protons is nearly 137 times stronger than the electromagnetic repulsion amongst protons. It is the most intense interaction indeed. However, this is just one possible way in which we can see the strong force. Too deep to move into this topic, we must study better the nucleus. At school, you surely have learned that the electron, proton, and neutron are fundamental particles. Well, if this is true for the first one, it's definitely not correct for the other 2. They are composed by quarks, which are fundamental particles. Protons are made out of 2 quarks, up and 1 quark down, while neutrons are made out of 1 quark up and 2 quarks down. The strong nuclear force between neutrons and protons is just small remnants of a much stronger interaction between quarks. So, the first interaction allows the existence of protons and neutrons and thus atoms. Finally, let's move towards the last but not least fundamental force that governs our world, the weak force. Like before, the name is not randomly chosen. In fact, the force is termed weak because its field strength over a given distance is typically several orders of magnitude less than that of a strong nuclear force or electromagnetic force. This interaction acts as a very small distances on subatomic particles and is responsible for nuclear fission and radioactive decay of atoms. Initially proposed by the famous Enrico Fermi in 1933, this interaction was successfully unified with the electromagnetic one in the so-called electroweak theory. Further developments are also expected from the GUT theory of great unification that aims to unify the electroweak and the strong interaction in a single electronuclear interaction. And it doesn't end here. A bigger task is that of the theory of everything, a name that you will surely remember from the famous movie about Stephen Hawking. The aim of this model is to collect the electronuclear force and gravitation in a single interaction that describes the entire world. So, we have seen that the 4 fundamental interactions can be reduced to 3 and probably less, and we have made a little highlight on their main characteristics. Now, we need to understand how the standard model catalogs all of them together with elementary particles. What are elementary particles? They are the smallest known building blocks of the universe. They are thought to have no internal structure, meaning that researchers think about them as zero-dimensional points that take up no space. Electrons are probably the most familiar elementary particles, but the standard model of physics, which describes the interactions of particles and almost every forces, recognizes 2 different groups, fermions and bosons. The first ones are characterized by half-integer spin. What does it mean? What is spin? It's really difficult to define this quantity, but in a very simplified way, we can imagine it as an intrinsic angular momentum of each particle. It doesn't have a classical counterpart, and even if it has the same units of measurement of an angular momentum, it's not associated with a real rotation of the particles around its axis. Fermions are divided in other two subcategories, leptons and quarks. Do you know what is the most common lepton of all? The electron. They participate in the electroweak interactions, and they are commonly organized in 3 generations. What does it mean? Electrons have 2 cousins with exactly the same amount of charge and spin, but a heavier mass. These particles are often called muon and tau. The possibility of observing the last one of these two are very rare, whereas the first one is usually produced when cosmic rays hit on the polar atmosphere of our Earth, generating exotic bunches of particles. Going on with leptons, for each type of negative charged particle, there is a neutral one, and it is called a neutrino. What are neutrinos? Since it has 0 charge, it just interacts through weak force and gravity. But its mass is so small that for a long time, scientists have thought that it was 0. We have a neutrino for each particular type of negatively charged particle. Scientifically speaking, we say that there are 3 different flavors of neutrinos, and so we call them the electronic neutrino, muon neutrino, and tau neutrino. These particles are probably the most difficult to observe as they rarely interact with matter, and they can even change their flavor. As an example, the Sun usually emits a lot of electronic neutrinos due to nuclear reaction in its core, but a part of them changes in tau neutrinos or muonic neutrinos in the journey to Earth. To complete the family of fermions, we need to describe quarks. Obviously, we have 6 quarks divided in 3 couples, each one linked to a particularly negative charged particle. We have quark up and quark down for electrons, quark charm and strange for muons, and finally quark top and bottom for taus. According to these definitions, we can organize fermions in 3 different generations respectively linked to their electrons, muons, or taus. Each generation has a negatively charged particle, its linked neutrino, and 2 quarks. Practically speaking, they differ just for mass, and we are still not completely able to explain why the matter we normally see is based on the first generation, since atoms are formed by electrons and protons and neutrons made up of quark up and down. As a matter of fact, the heavier leptons are not so stable. For example, the muon has an average time of decay of just 2.2 times 10 to the negative 6 seconds. Obviously, you'll have heard about antimatter. What is it? It's a matter formed by antiparticles. Each fermion has a counterpart with the same value of mass and spin, but opposite. Furthermore, we need to deal with bosons. What are they? Their name was coined by the genius Paul Dirac, and they are the force carriers of the 4 fundamental interactions with a spin equal to 1. What is a force carrier? It seems really difficult, but if you've paid attention, you'll notice that we have already mentioned an example of a force carrier. Do you know what it is? The photon. In fact, this particle with 0 mass is the carrier of electromagnetic interaction. When a UV ray hits an atom, it's the photon that is absorbed, giving a great energy to the electrons that may get into an excited state and return to their fundamental one after a few seconds, emitting another photon. Together, with this one, we have other 3 vectoral bosons, gluons, which are classified into 8 different types that carry the strong interaction W, that can be W plus or W minus, and Z, that are the intermediators of weak interactions. It's difficult to explain why in a few lines, but this whole theory needs a scalar boson with 0 spin called Higgs boson that gives mass to all other particles. The evidence of the existence of such a boson was definitely proved in 2012 at CERN with the CMS experiment after the first theoretization in 1964 by Peter Higgs. The researchers working in Geneva, Peter Higgs and Francois Englert, were given the Nobel Prize in 2013 for this exceptional discovery. Therefore, the existence of one last tensorial boson with spin equal to 2, called graviton, carrier of gravitation, is what could complete the model. However, we have had no evidence of such a particle, and further research must be made in order to give a proper structure to the standard model. Great problems such as dark matter and dark energy still need to be solved, and we must elaborate more and more models that can try to explain such phenomena, even if this means going beyond the famous Standard Model. Thanks for watching, everyone. Are you amazed by the 4 fundamental interactions? Do you want to know more about a particular type of particle? Have you ever heard about fermions and bosons before? Let me know in the comments below. Be sure to subscribe, and I'll see you next time on the channel.